Hello guys and gals, welcome back. In this video, we're going to be talking about 5.1b, in which we're going to be talking about the relative rates of reactions and the rate of appearance and the rate of disappearance. So one thing to keep in mind before we get started is that rate is not the same thing as concentration, okay? So rate and concentration are related. Rate is dependent upon concentration, but they are not the same thing, okay? All that concentration is going to do is going to help us get a picture of what the rate is doing, but they are not equivalent, all right? Now that we know this, one thing to address before we get started is that both the rate of appearance and the rate of disappearance are solved the same way. They're both solved with this rate is equal to change in concentration over change in time equation. There's no difference between them, okay? They are solved the same way. The only difference is that the rate of disappearance is going to have a negative slope. If you're going to graph it on a concentration versus time graph, it's going to have a negative slope. And the rate of appearance is going to be positive. If you're going to graph it on a concentration versus time slope, you're going to see a positive slope. So in this example here, it's a great example because it shows us both. Now this is a concentration versus time graph. And like I said, concentration is not equivalent to rate, but this is the exact relationship that the rate law gives us, concentration over time. So we can look at this graph to help us determine how the rate is changing throughout the equation, or throughout the reaction. We can see here that line A is decreasing, but it does not decrease steadily. And that makes sense because rate is not constant throughout the reaction. As our number of molecules, or if we're in 1 liter, that can be equivalent to our concentration. So as our concentration decreases, our rate is going to get slower and slower and slower. And so we're going to see the same thing with our rate of appearance of our products. Right here, we see that at first we make lots of products very quickly, and then we start to slow down and slow down and slow down. We're still making products, but it's getting slower and slower and slower. So we see this exponential kind of graph instead of a straight line. But we do see that the rate of disappearance of our reactants is negative, and the rate of appearance of our products is positive. So do keep in mind, pay close attention when you are on the AP exam that you do read that y-axis. Sometimes they can really ask you some trick questions and they'll give you the number of molecules instead of giving you concentration. Be very careful for that, okay? So the rate of appearance and rate of disappearance, we can solve for them like physical, numerical, this is what it actually is. But we can also solve for the relative rates of appearance and disappearance without any actual data. Relative means in comparison to each other. So we can use the coefficients in the balanced chemical equation to compare the relative rates of our reactants and our products. Let's use this example to help us out a little bit. Okay, so from this balanced equation, we can compare the relative rates of appearance and disappearance for each species involved in the reaction. And a species is just a compound, a chemical, a particle, whatever. All right, so what we can see here is that for every 2 moles of nitrogen dioxide that we use up, we're gonna produce 1 mole of oxygen gas. And so rate-wise, relatively, we can say we're going to produce oxygen half as quickly as we're going to use nitrogen dioxide, or that oxygen gas is going to appear half as quickly as nitrogen dioxide disappears. We can also compare the 2 products to each other. So we can say for every 1 mole of oxygen that's being produced, 2 moles of nitrogen monoxide are being produced. And so we can say nitrogen monoxide is being produced twice as quickly as oxygen gas is. Or that the rates of appearance, or the ratio between their rates of appearance relatively, is 1 to 2. Nitrogen monoxide is going to get produced twice as quickly. And oftentimes people are going to summarize what I just said basically in this kind of format. And this can look really scary at first, but if we break it down, it's not too bad. Okay, so initial rate of reaction means the reaction at the very beginning of the rate at the very beginning of the reaction. Time is equal to 0. What is the rate going to do? This whole big thing is where it starts to get complicated. So let's just break it down one thing at a time. change in concentration of NO2 over change in time. Well, that's just rate. That's all that is. That's just rate. This is the rate of disappearance, and we know that it's rate of disappearance because there's a negative sign right here. This is the rate of disappearance of nitrogen dioxide. And relatively, it's going to be equal to the rate of appearance of oxygen gas and of nitrogen monoxide. So this fraction here with the deltas in it, that's literally just saying rate of that compound. That's all that it is. Now these fractions here, they look complicated, but in all actuality, all they did was take a 1 and stick it over the coefficient. That's all they did. Basically, what this does mathematically is it helps make sure that our ratios stay the same when we start comparing different amounts of these to each other, okay? I'm not a math person. I really don't know much beyond that. I know that it helps us keep our ratios the same, okay? So all we're going to do when we're talking about relative rates is we're going to put 1 over the coefficient, and then we're going to set these rates equal to each other. Because if everything was in a 1-to-1 ratio, then the rate would be the same. The relative rate would be the same, right? But if it's not, we put these little fractions in front of it, 1 over your coefficient, and there you go, we can solve it. So let's do an example to see what that looks like because it can be confusing. And this example is going to come directly from one of our AP sample tests, okay? So referring to this big, long, complex equation right here. At a certain time during a titration, the rate of appearance of oxygen gas was 1.0 times 10 to the negative third moles per liters times seconds. Okay? That's the rate. What was the rate of disappearance of permanganate at the same time? Okay, well, how do we solve this? They've given us the rate of oxygen gas, and they've given us the balanced chemical equation, and they've given us nothing else. That's literally all we have. If you come across a problem like this on the AP exam where all you have is the rate of 1 or 2 things and no experimental data, but you do have the balanced chemical equation, that's going to be a big flashing neon sign right there that you're going to have to do relative rates. Okay, so let's solve for it. I'm just going to do the same setup that they did in the previous picture. They had, this was rate of appearance, so it was positive, and then they put 1 over the coefficient. The coefficient in front of oxygen was 5. And then they just put the rate of oxygen here, so 1.0 times 10 to the negative third. And then they set that equal to the relative rates of everything else. In this case, I only care about permanganate, so I'm going to do negative because it's the rate of disappearance. The coefficient in front of permanganate was 2, so it's negative 1 over 2. And I'm going to put an X here for the rate of disappearance because that's what I'm solving for. And then I'm just going to solve for this algebraically. Nothing too complex beyond that. 1.0 times 10 to the negative third. We're going to get 2 times 10 to the negative fourth is equal to negative 1 over 2x. And then we'll divide by half. And we get that the rate of disappearance of permanganate is 4 times 10 to the negative fourth. So let's talk about what I did. The only thing I had was the balanced equation and 1 rate, so I knew that I had to use relative rate to solve for it. Relative rate is where you just take the rate of everything, you set it equal to each other, but then in front of it, you put 1 over the coefficient from the balanced chemical equation. And then I just solved algebraically. That's all that I did. Now this negative here, you might be like, well, why isn't that negative? Because the only thing that negative indicates is that this is the rate of disappearance. Okay, my rate is not really negative. If I were to graph it, it would show me a negative slope, but this is just showing me the rate of disappearance. Okay, and that's answer choice D. And that's pretty much all we have for this section. Okay, so let me know if you guys have any questions, and I'll see you next time. Maybe. There we go.